Hello, this is Teresa Stack, Assistant Professor with Montana Tech at the University of Montana, and this is the second part of Lecture 4, Descriptive Statistics or Descriptive Epidemiologies, Measures of Disease Frequency. So our objectives are exactly the same as they were in the first part. This just continues the lecture. I think it's nice to break it down into pieces so you don't become too overwhelmed by all of the material at one time. This slide is the start of your equation sheet. So we started to talk about numbers in the last couple of lectures. We talked about proportions or attack rates, ratios. We looked at crude rates, adjusted rates, stratified rates, and we talked about prevalence, point prevalence, and period prevalence as well. And so this lecture will focus a little bit more on incidence, but we'll do some calculations together. So this is just an example of how you might be able to prepare for assignments or exams that you may see in the future. So incidence is a rate because it's over a specific time period versus a ratio which isn't over a specific time period. And it's the number of new cases or events that develop in a population over a certain period of time. It's actually quite useful because it's the measure of the probability that a healthy individual will develop the disease during a specific time period. And for many of these incidence cases, we try to define a population and then follow them over a time period and see who develops the disease versus who does not. But you can also, of course, do this retrospectively by reassembling populations, and we'll talk a little bit more about prospective and retrospective sampling. So there are two different types of disease events or states. One is acute and one is chronic. And so incidence looks at things a little bit differently. So when you have an acute event, so something that happens over a short period of time, the cases in which you count, or the injury events, are new within this particular time period. If the disease reoccurs, the same person may experience the disease more than one time, which means that you would count them more than one time within a specific time period. Or if it's chronic and it takes a while for a disease to develop over a specific time period, each person is only counted once. So a chronic disease, you have a short time period in which the disease develops. If people get it multiple times, we count them multiple times. So an example may be blisters on the feet, right? Something easy. You can have multiple blisters in the course of a year. And then directly contrast those to a chronic disease such as lung cancer. Your time period will be much longer in which it takes new cases to develop in, and therefore every person is only counted once. So what kinds of data sets do we need to calculate incidence? Well, we need to know the current knowledge of the study population, either based on screening or historic data. And then what is the time of onset at that specific disease? Sometimes it's easy to know. You go to the doctor and you're diagnosed, you get medication for something like influenza, but it could be more difficult for things like cancer or chronic occupational illnesses where we're really not sure when there was a physiological change to the body and the symptoms start to manifest themselves. And that's your point in time in which you become a case. As with much of our calculations that are done in EPI, we really need to know our denominator, the number on the bottom, and our numerator, the number on top. So when we talk about our denominator, that's our population. Because this is a rate over a study period, and populations change over time, we usually use the midpoint of that study periods population. So if it was 12 months, then we would use the end of May as our midpoint in our year, or we use the average population over a length of time. Now our numerator needs to be very specific as well. Are we counting people who repeatedly have an event, or are we counting the event itself? So an example here was there's a specific difference in a year's period of the number of people who develop a cold versus the number of colds. Because a person can develop a cold more than one time, and therefore they can be counted more than once if we're considering this our chronic exposure. And so you also need a period of observation, whether it's a year, 2 years, 10 years, a couple of months, and that's what makes this a rate. And here is our formula. So let's take an opportunity to do a calculation together, and we will try to calculate the incident rate of pertussis or whooping cough in Montana in 2013. So it would be the number of cases divided by the population and if we do our math, we would come up with an incident rate. And to make the incident rate normalized for a certain group of people, and we do this a lot, either we try to normalize our rates by 1,000 people or 100,000 people so that we can compare it to other populations. Because Montana, we usually use, 100,000. And it would give us an incident rate of 65.3, which means you're 65.3 times more likely to develop whooping cough per 100 residents in the state of Montana. And what's really interesting about this figure is that, let me put the, if we go to the next slide and doing the calculations, the overall U.S. rate is 7.7 per 100,000 U.S. residents, and Montana is at 65 per 100,000 U.S. residents. So we have a significant incident rate of whooping cough in the United States, which far exceeds that of the rest of the United States. So let's do a couple of more calculations together to get you used to looking at incident rates. So mortality rates is a way of, also another word for an incident rate, because you only die once. What's the percent increase in the number of deaths, and what's the percent change in the incident rates in the number of deaths between a certain time period? So we're looking at between 2 years. So the first thing we want to do is set up our equation and get our data lined up. So we have in 2013, divided by our population. Oops, sorry. Oh, that didn't go well. Okay. And we have our incident rate. And then we do the same thing for the previous year. And hopefully by doing it this way, you're able to see where the numbers are coming from. It's hard for me to talk and do math at the same time. So now we've been able to calculate our two incident rates. Oh, there is definitely a typo in there. Well, you see where that number came from. I don't know how to click in that box and make that change. Otherwise, I would. So if we go to the next slide, here it's on the next slide. I just did my division wrong a little bit there. So this would be the mortality rate, the incident mortality rate. So now the question is, what is the percent change in the number of deaths in Denver? And so to calculate percent change, we just do a calculation using our incident rates. So we had 21.4 incidents in 2013, and we'll subtract that from our incident rate in 2012, and we come up with our difference. And then we take our difference in our incident rates and we divide it by our 2012 number, because we're going from 2012 to 2014, so we want to see the difference, and that's why in the subtraction we take the first number's incident rate and we put it at the bottom, and we find out that there was a 70% change, there was a 70% increase in the incident rate from one year to the next year. Sorry about that, didn't mean to move ahead. I thought I put a blank slide in there when the math was done a little bit cleaner for you, but I think you can see the math anyways. And now we're looking at what is the percent change in the number of deaths. And so our first calculation that we do is we take our number of deaths and we subtract one from the other. So we take our 2013, we subtract it from 2012, and we find out that the difference in our number of deaths was 540. That's our difference. And we want to see what the percent change was from the start of 2012 to 2013. So we take our difference between our 2 years and then put it again against our primary year's number. And we see that there was an 80% increase in the incident rate and an 85% increase in the number of deaths. So both numbers are going up at the same time, which we would expect them to because we're just playing one number off of the other. But I think that it gives you the opportunity to see how different numbers are displayed in different ways in a population. And so this gives you the calculation for the percent change in incidence, and this is a summary of both of them. So we're talking about the number of deaths that we had. We saw an 85% change in the number of deaths, but we saw a 70% change in the mortality rate, the incident rate of the deaths over a year's period. Counting cases versus using rates. Okay. There are two types of incident rates. One is cumulative incidence and the other one is incident density. And so I have two charts here so you can look at the difference in the way the data would be displayed. Cumulative incidence measures a proportion or the magnitude of what is occurring in our population, where incident density is related to the rate or the intensity, as in how fast it's occurring in our population. And I think if we do some calculations here, you'll be able to see the difference in where it's used. The advantage of using incident density is we try to estimate person years, and that could be quite useful if we cannot study people over a long period of time. So cumulative incident is your proportion of your disease over the time. It's the number of new cases, or incidents we call them, during a given time period, and the total population at risk of that time period. So we just calculated cumulative incidence, but we're putting a label on it and then helping you define that before we calculate incident density. Persons at risk at the start of the event, that's the person that we count. We try to observe the person for the entire observation period. Cumulative incident is a proportion. It's not actually a rate because the numerator, the people in the numerator, are also included in the denominator. Remember, cumulative incidence of a disease, we must have our specific time period, and it estimates the probability that a person chosen at random from our specific population will develop a disease within a specific time period. So we're going to take a look at some data here, and let's say that we started following all the subjects in January. Oops, sorry about that. In January of 1999, and this indicates that that's the period in time in which the person developed their disease. And if there's no data, and so we followed them from the start of the study to the period of time in which the person developed their disease. And so the question is, and I gave you the answer on the other side, what is the cumulative incidence for the 4-year study period? So our cumulative incidence for our 4-year study cases, which would be how many people developed the disease, 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 people developed the disease, divided by our average population in that time period, which is 500. And then we're able to calculate our cumulative incidence, which is 0.00. You could probably do this faster on your calculator. So the number of new cases during a study period over the total population at risk during a particular time period. And this is our cumulative incidence. Cumulative incidence assumes that we're able to observe the entire population over our study period. And sometimes that's hard because people enter and leave our population. The problem with cumulative incidence is we don't always get the opportunity to observe people throughout our entire study period. And so the way that we fix that is by using incidence density. Incidence density is calculated by using the number of new cases during a time period, so the numerator is exactly the same. But this is our denominator. We do a little math with our denominator and we adjust it. So instead of over the total time or the average time that we're observing our population, we change it into person time years. Person time at risk is a specific amount of time over which each person is observed. Incidence density is a rate and it is not a proportion. And it's really hard to compare rates and proportions. So if we go back to cumulative incidence, cumulative incidence is a proportion of your population that develops the disease. Incidence density is the rate at which the disease is developing in a fixed population, or the speed in which the disease is developing. So now we have exactly the same data, but we followed people for different periods of time, and that's what this column is how many years did each person contribute to the data. So this person contributed 2 years, and this person contributed 1.5 years. And then we're able to use this data to calculate our incidence density. So we calculate our incidence density. Let's go back. So how many people developed the disease during our study period? We need this first as our numerator because this is the number of new cases. So we count 1, 2, 3. 3 new cases during our study period. And so our numerator is 3. And our denominator is our person time, and our denominator is our person time years. So we add up all the person time years. So it was 1.5 plus 2 plus 4 plus 2 plus 3.5, and I'll show you where that data came from, plus 1 plus 1.5 plus 2. And that equals 17.5 person years. And that becomes our denominator. So where I got the years is that I added all these numbers up, and this row became my, I always think incident density, D as denominator. This became my denominator. And our math is 3 new cases over 17.5 years. And it gives us an incident density of 17.1 cases per 100 person years. Because I multiplied the fraction by 100, or the incident density would be 0.17 cases per 1 year. Incident density also has another name. It's called force of morbidity or hazard rate. The total number of person time units does not represent a total number of individual observations. So the sum of 100 person years does not represent that we observed 10 people for, that we observed 10 persons for 10 years. We could observe 20 persons for 5 years, or some other way to come up with our 100. Second, there's an assumption that the risk of disease or death is constant throughout the entire study period, which may or may not be true. You're at different risk factors for different diseases depending on where you are in your professional career, where you are in your life, what your health is likely to be. So what do all these numbers mean? So I thought I'd go through and I'd do something to look at the data in just one more different kind of way. And so I was just trying to be funny with marijuana is safer than peanuts, right? Because the annual deaths from marijuana are 0 and the annual deaths from peanuts are much higher. But so the question is, what does a crude annual death rate, so this is a rate, we know it has to do with incidence, of 8.4 per 100 people actually mean? Well, this is pretty easy. Like, we can first look at it and we know that it means that about 9 out of every, let me change this. I think it'd be easier if I did it this way. Easier for you. Okay, it means that 9 out of every 1,000 people in our community died. And we can see that really clearly from the data. And 864 people died per 100,000 people in our population. It also means that the risk of dying is about 0.9%. And that so what is our crude death rate? Our crude death rate is 0.86%. So I have a proportion question for you to look at also, to look at the data in different types of ways. So the following statement was made in a newspaper article, and it was sought to provide data bearing the use of seatbelts in preventing deaths in automobile crashes. Of the 649 people who died in traffic accidents in Montana last year, 55 were not wearing seatbelts. In those same fatal crashes, 73% of the people who were belted in survived. So does this statement support the hypothesis that seatbelts help save lives? So the answer is we really don't know, because how many people were in car crashes that were belted in and lived, and how many people were in car crashes that were not belted in and lived. And so it leaves us wondering what the data really looks like. And that when we're comparing percents, we really need to have data on all 4 aspects, belted and unbelted versus dead and alive. Thank you very much for your time, and I hope you have a pleasant day.